Hi everyone, in this video we are going to discuss this example. So here we have a set A. We have to prove that it is compact subset of R to D where D is a Euclidean distance. So here I have written a given information. The first and very important information is the metric space R to D. D is a Euclidean distance, and the second information is this set. We have to prove that it is compact. So let me mention here, to prove that A is compact. So we have to prove that it is compact in this metric space R to D. So let us discuss what is this set. Okay. See, here we have mod x plus mod y less than or equal to 1. So when we want the region, first we should replace inequality by equality. That means mod x plus mod y is equal to 1. We are familiar with the definition of mod. So the definition of mod is x if x greater than or equal to 0, and it is minus x if x less than 0. It means the value of mod x is either plus x or minus x. Similarly for mod y also, its value is plus y or minus y. So if you consider all these cases, we will have 4 different lines. If x and y both of them are positive, then we will have x plus y is equal to 1. If x negative, y positive, then we have this line. X positive, y negative, and the last case is both of them are negative, right? So x plus y is equal to 1. That means a line which passes through these 2 points 1, 0 and 0, 1. Similarly, for remaining 3 equations, we will have lines like this. Okay, so let me draw. So yes. So as you know, okay, just a minute, let me draw properly. Okay, so as you know, here they have mentioned mod x plus mod y less than or equal to 1. That means it indicates the region which is bounded by these 4 lines. So that means this is the region we have. Okay, so bounded by these 4 lines. So we get a square here. And now we have to prove that it is a compact set. Okay, so let me remove the unnecessary part so we can continue and we will have some more space to write. Okay. See, one result we have already seen, let me mention here, in R to D. So that result is specially for Euclidean space. So that result is a set is compact. Set is compact if and only if it is closed and bounded. So the result is very simple. That means if the set is compact, then it is closed and bounded. And in a reverse way also you can say if the set is closed and bounded, then we can say it is compact. So here what we have to do, we have one set and we have to prove that it is compact. So if you use this result, we can simply say we have to prove it is closed and it is bounded. So here also we will do same. We will first prove that the given set is bounded, and then we will prove that the given set is closed. So let me mention here, that is to prove that A is closed and bounded in R to D. So this thing we have to prove. Okay, what we have to prove, the set is closed and bounded. So first we will prove that it is bounded. First we will prove that A is bounded. A is bounded. So now the question is how to prove the set is bounded. So there are different techniques. The first technique, okay, just a minute, let me remove this part. So the first technique is, we can prove A is subset of some ball with center 0, 0 radius r. Okay, A is subset of ball for some r, greater than 0. So this is first technique. The second technique is if you take any point xy belongs to A and norm xy is less than or equal to some m, getting it is less than or equal to some m, where m is positive real number. So in this way also we can prove the set is bounded, or we can use the first technique also to prove the set is bounded. So here I am going to use the second technique. I am going to prove the norm of any point of A is less than or equal to some fixed positive real number. So let us prove. Let us take one point from A, let xy. I am taking any point from A. So xy is in A, it means it satisfies the definition of A, and the definition of A says mod x plus mod y is less than or equal to 1. So this is so much important information we have got, so I am calling it as star. We are going to use it later, okay? Just a minute. See, the diagram and that thing is not required, so let me remove it now. So let us consider norm of xy, okay? So let us find. So consider norm of xy is equal to, so we are familiar with the definition of norm, which is square root of x square plus y square, right? See, I will take square of both sides to remove square root. So it will be norm xy square is equal to x square plus y square. See, you know that square, that means always it gives the positive value. So if you apply mod, we will have the same value, mod x square plus mod y square. Actually, there is no need of mod. If you apply mod, then also you will have positive value. If you don't apply, then also you will have positive value. But it is a part of adjustment. So that's why I'm using mod here. If you add some positive real number or non-negative real number, then we will have this is less than or equal to mod x square, mod y square plus 2 mod x mod y. So this is additional part, I am adding. So the value will get increase. If x and y are 0 or one of them is 0, then we will have equality also. See, do you remember anything by observing this? It's a bracket square, right? It's a bracket square. It is bracket square of what? Mod x plus mod y whole square. It means we get norm xy square is less than or equal to this inequality we got here, whole square. Let us take square root of both sides. So norm xy is less than or equal to, I am taking square root, so square root will get cancelled, mod x plus mod y. But see, our star inequality star says mod x plus mod y less than or equal to 1. So this is less than or equal to 1. So therefore norm xy is less than or equal to 1 for all xy belongs to A, since it is any arbitrary point of A. So in this way we proved that set A is bounded. Therefore A is bounded set. Okay, so in this way we prove the set is bounded. Now we have to prove that the set is closed. Make a screenshot of it, then we will go further. See, now we have to prove the set is closed, right? So how to prove the set is closed? So there are several definitions. We can prove complement is open, then also we can say the set is closed. We can prove if the set contains all its limit points, then also the set is closed. One more definition is there, if A is equal to A bar, then also we say the set is closed. So the third technique I am going to use, I am going to prove that A is equal to A bar. Let me mention here, that is to prove that A is equal to A bar. We have to prove these two sets are equal. That means we have to prove the first set is subset of second and the second set is subset of first. So I think one thing is obvious, that is A is subset of A bar. So clearly A subset of A bar, equation 1, statement 1, getting? So let me tell you why. Since A bar is nothing but A union A dash. So A bar is formed by taking union of A and A dash, so obviously A is subset of A bar, getting? So the first thing is obvious. Now to prove that A bar is subset of A. Now to prove that A bar is subset of A. So that means we have to take one point from A bar and we have to prove that it is in A, then we can say A bar is subset of A. Let us take one point, let PQ, I am taking one arbitrary point, belongs to A bar. See, there is one result which we have already proved. If you have any point from A bar, it means there is a sequence of points of A which converges to this point. So that thing I can use here. So therefore there exists a sequence, we get a sequence basically xn y of points of A such that getting, so that sequence xn comma yn converges to PQ. Getting this result already we have proved, that is we get a sequence xn yn of points of A, this is very important thing, and which converges to PQ. Okay, we have a space, so let us use. So we are familiar with some basic results of sequence. If you have any sequence like this xn yn in R2 converges to PQ, it means the first component, sequence of first component converges to the first component, and sequence of second component converges to second component. It means xn converges to P and yn converges to Q. See, there is one more result of sequence. Getting, so there are several results of sequence I am going to use now. If you take mod of xn, then it will converge to mod P, and mod of yn converge to mod Q, right? If we have two convergent sequences, xn converges to x, yn converges to y, then their sum xn plus yn converges to x plus y. So using that result we can say mod xn plus mod yn. Tell me where it converges? It converges to mod P plus mod Q. Getting? So let me write it properly. Okay. See, but basically xn yn, this is sequence in A, right? This is sequence in A. So this is sequence in A. It means it satisfies the definition of A. The definition of A says mod of xn plus mod of yn less than or equal to 1. Getting? By definition, since it is an element of A, so it will obviously satisfy the definition of A. But the second thing is mod xn plus mod yn converges to mod P plus mod Q. Here we have already written. See, if this is less than or equal to 1, then the point where it converges, that is also less than or equal to 1. So therefore mod P plus mod Q, that is also less than or equal to 1. So that means the condition is satisfied again. Getting? So PQ satisfies the condition of A. So therefore PQ is an element of A. You remember the beginning, we started one point PQ from A bar and we finally proved that it is in A. So therefore that A bar is subset of A. Statement 2. 1 says A is subset of A bar, 2 says A bar is subset of A. Let us combine 1 and 2. So 1 and 2 gives A is equal to A bar. Getting? A is equal to A bar means what? The set is closed. So therefore A is closed. Getting? So in this way we proved the set A is bounded as well as it is closed. So finally we can declare therefore it is a compact subset of R2, right? Make a screenshot, then we will go further. So therefore I have written a conclusion here. Conclusion is the set A is closed and bounded subset of R2D, where it is a Euclidean distance. So therefore by using that result we can say A is compact subset of R2D. Okay. So make a screenshot of it, then we will stop. Thank you. See you.